Hi, I'm Jonas, representing Abwasserverband Braunschweig, a wastewater association located in the middle of Germany. And here I'm responsible for coordination and organization of national and international research projects like the NextGen project. Within the NextGen project, we work strongly together with KWB, who takes care of the scientific support regarding data analysis and evaluation. Here in Braunschweig, at the demo site, we run a wastewater treatment plant receiving domestic wastewater from about 350,000 population equivalents, and the plant consists of a conventional primary and secondary stage with an activated sludge process and an anaerobic sludge treatment afterwards. So last year in October, we started with commissioning of a new full-scale sludge treatment system, which combines a nutrient recovery system for nitrogen and phosphorus with a thermal pressure hydrolysis, which is integrated in the digestion process of the excess sludge. So the new system produces, on the one hand side, recovered fertilizers, which can be used by local farmers. And on the other hand side, the thermal pressure hydrolysis leads to increased methane yield during digestion and an improved dewatering process afterwards. Moreover, the thermal pressure hydrolysis increases the concentration of dissolved phosphate and nitrogen, which thereby are available for the recovery process. In terms of how the new technologies in Braunschweig fit in within the circular economy approach, we can see that we have an increased biogas production within the energy circle, which can be used for electricity and heat production, and that we produce recovered fertilizers within the nutrients and material cycle, which can be used by farmers or industry. So let's take a closer look on the technology unit of the thermal pressure hydrolysis. As I said before, the technology is integrated in the digestion process of the excess sludge. So after the first digestion stage with mesophilic conditions, the sludge is given to the thermal pressure hydrolysis, where the sludge is cooked at a pressure of about 4.5 bar in the pressure reactor. And in the following economizer reactor, the pressure is decreased via a rapid decompression to about 0.2 bar, and thereby the cell walls of the microorganisms are destroyed, and thereby volatile carbon compounds are released, which leads to an increased biogas production afterwards. On the next slide, we see the full-scale technology for phosphorus recovery, which produces struvite. The technical unit receives liquor resulting from the dewatering process of the digest via centrifuges. And in order to produce struvite, the pH of the liquor needs to be raised to a level of 8 and higher in the first step. Therefore, CO2 can be removed from the liquid phase via air stripping, and afterwards, within the second reactor, the precipitation of struvite can be induced by adding magnesium chloride, which reacts with phosphate and ammonium to form struvite. So, as you can see, first samples of the struvite show a very clean and pure product with very fine crystals looking like sand. In the next step, the effluent of the phosphorus recovery unit is given to the nitrogen recovery unit, which produces an ammonium sulfate solution. Therefore, the ammonium-rich liquor is first stripped with air at a temperature between 55 and 65 degrees and at a pH between 9 and 11. And under those conditions, ammonium reacts to ammonia gas and then can be easily stripped out via air stripping. So afterwards, in the following gas scraper, that is the second column, the ammonia gas reacts with sulfuric acid to ammonium sulfate. And ammonium sulfate is a typical nitrogen fertilizer. Regarding the possible flow rates, we can say that the thermal pressure hydrolysis can treat up to 12 tons of dry matter per day, and the nutrient recovery units can treat up to 25 cubic meters per hour. Okay, so that was a lot of technical information. Let's now take a look on the first results regarding energy management and nutrient recovery efficiency. Here on this slide, you see a graph showing the sum of methane produced in the 3 sludge digesters of the plant here in Braunschweig over a period of 1.5 years from the beginning of 2018 until spring 2020, when the thermal pressure hydrolysis was stopped due to COVID-19 issues, unfortunately. As you can see, the sum of the produced methane increased from the start of the thermal pressure hydrolysis on, compared to the period without the additional sludge treatment. So in total, we expect that we can increase the production rate of biogas up to 25%. If we take a closer look on the organic loading rate of the treated sludge in that period, we can see that we have a continuous fluctuation of the organic loading rate between 1 and 3 kilogram dry matter per cubic meter a day. So thereby we can state that increased biogas production is not a result of increased organic loading rate, but is caused by the thermal pressure hydrolysis itself. Now let's leave the energy management and let's go to the nutrient recovery efficiency. We start with the phosphorus recovery. On this slide you can see a graph showing the phosphate concentration of the inflow of the recovery unit in green and the concentration of the effluent in green-white over a period of several days in which the unit operated continuously. So the average recovery rate was about 50%, which is far too low compared to the expected recovery rate of 90%. Reasons for that might be the small crystal size growth, which leads to washed out struvite crystals, which didn't or couldn't settle down for separation. Another reason might be over or underdosing of magnesium chloride. So the right adjustment of the chemical process is very complex and time intensive. Now let's take a look on the nitrogen recovery unit. In red you can see the concentration of ammonium of the technical unit's inflow, and in red-white the concentration of the effluent over a period of several weeks in which the recovery unit operated continuously. We can see that the average recovery rate in that period is higher than 90% and also higher than expected. The recovery process seems very stable and efficient, and regarding further optimization, we currently try to reduce the recovery rate to some extent in order to save energy and chemicals. What have we learned so far here in Braunschweig? Regarding the thermal pressure hydrolysis, we made the experience that the technical unit is very maintenance intensive and needs a very high gas quality for the steam generator. But on the other hand side, an increase up to 25% is possible regarding the biogas production. The phosphorus recovery unit needs a very low concentration of suspended solids, under 600 milligram per liter, and the chemical adjustment of the precipitation process needs a lot of time in order to receive crystals with the required size of 3 millimeters. Regarding the nitrogen recovery unit, we can state that the technology is well established and very safe, and very high recovery rates are generally possible. As the single technical units are connected in series in Braunschweig, the operation efficiency of the units depends to some extent on each other, which makes operation more What have we planned for the next year in Braunschweig? Well, in the next month, we plan to optimize the phosphorus recovery and struvite production regarding crystal size and recovery rate via changing various operation parameters like retention time or chemical dosing. Regarding the nitrogen recovery unit, we will further try to reduce energy and chemical consumption, as I said before. And with focus on the heat and energy management, we will further analyze the internal energy production and consumption caused by the thermal pressure hydrolysis, which is integrated in the digestion process. So many thanks for your attention.